1968 was a year of turbulence the world over.
In America, Martin Luther King and Robert Kennedy were assassinated.
Senator Kennedy has been shot. Is that possible?
General strikes shut down France, and 1 million students marched in the streets of Paris.
And the war in Vietnam raged on.
Okay, try and bring him back here. Remember to stop the
But something else monumental happened towards the end of that year, and it had to do with an entirely different domain.
We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they
The Cold War-fueled race between the Soviets and Americans for space supremacy was in full swing. And by all accounts, the Soviets were winning. They'd put the first satellite in orbit with Sputnik, the first man in orbit with Yuri Gagarin, and conducted the first spacewalk.
But in an effort to prove America's power, the US government was determined to be the first to put a man on the moon and bring him back safely.
As a major step towards fulfilling that goal, NASA was preparing to send 3 men,
Frank Borman, Jim Lovell, and William Anders,
into space to orbit around the moon. The mission was Apollo 8, and if successful, it would be the first time that human beings left Earth's orbit and headed to another celestial body. And so on the early morning of December 21st, Apollo 8 sat on the launch pad, preparing to take off.
I remember it quite well because I was the last man to get into the capsule.
That's Apollo 8 astronaut Jim Lovell.
It was still dark, and as I was waiting on top of the gantry, which was about 370 feet tall, I suddenly looked down and saw the lights of the media, and I realized that this was not just another Earth orbital flight, but actually we are all very serious about going to the moon.
20 seconds, all aspects, we are still go at this time. 10, 9, we have ignition sequence start. The engines are armed. 4, 3, 2, 1, 0. We have commit, we have liftoff. Liftoff at 7:51 a.m.
It took the crew 3 days to travel the some 380,000 kilometers needed to reach the orbit of the moon. And on Christmas Eve, 1968, millions of people tuned in for what was then the most watched moment in television history.
How's your picture quality, Houston?
This is phenomenal.
Welcome from the moon, Houston.
Thank you.
The astronauts pointed the camera through the module windows to show viewers the surface of the moon that lay below.
I hope that all of you back on Earth can see what we mean when we say it's a rather foreboding horizon, a rather dark and unappetizing looking place.
But the real thing of lasting significance that would happen during the Apollo 8 mission, the thing that it's still most famous for publicly all these years on, came a little earlier that same day when the TV cameras were off. And it was something that neither the crew on board nor the commanders at NASA had prepared for.
A few minutes after 10:30 a.m. Houston time, as Apollo 8 came around the far side of the moon for the 4th time, Commander Frank Borman began to maneuver the module according to the flight plan, rolling it around on its axis.
And as they orbited around the moon, they saw an amazing sight through their windows.
The Earth started to appear above the lunar horizon.
Oh my God, look at that picture over there. There's the Earth coming up. Wow, that's pretty. You got a color film, Jim? Hand me a roll of color quick.
Oh man, that's great.
Where is it? Quick.
They rushed for their cameras and started snapping pictures.
Just grab me a color. A color exterior. There you go.
For the first time in history, human beings were witness to not a sunrise or a lunar rise, but an Earthrise.
Hey, I got it right here. Take several of them. Here, give me. Wait a minute, let me just get the right setting. Hey, calm down, Lovell. Oh, I got it right. Oh, that's a beautiful shot. 250 at F11.
The astronauts were supposed to take pictures of the lunar surface to help find suitable landing spots for future missions. But suddenly, it was Earth, that planet that they had just come from, that was much more interesting.
This mission was the first time human beings had seen the Earth in its entirety, as a small, round blue planet nestled in the infinite darkness of space.
You can see the blues of the oceans, the whites of the clouds, the sort of browns and tans of the desert areas. And when I looked at the Earth from this point of view, I could put my thumb against the window of the command module. I could completely hide the Earth behind my thumb. That's how small it was. And I realized that when I put my thumb up there, that everything I ever knew in my life was behind my thumb. And that included around 5 billion people living there, and all the history of the planet that I'd ever known, and my loved ones, and everything like that. Everything was behind my thumb.
Back on Earth, after the Astronaut's film was developed, the rest of the world too got to see Earth from this point of view. One of those images became the famous photo called Earthrise. It was the first published image of the whole Earth ever taken by humans. It showed the desolate lunar landscape in the foreground, looking gray and forbidding, and behind it, surrounded by black space, the beautiful blue marble called Earth.
Before this, no one had seen the entire Earth before. Sure, we'd known we were on one planet.
But suddenly, with this photo, it was viscerally clear that we humans were part of something much more complex. It was now understood, not just in an abstract sense, but in an emotional, even spiritual way, that we were all on the same ship, passengers on spaceship Earth. This is The Elephant, with me, Kevin Caners.
And me, Charlotta Lomas.
Coming up, we go on a journey to explore our planet and find out how one species, Homo Sapiens, ended up changing everything.
Kevin, I find that Apollo mission so fascinating.
Me too. It seems rather poetic that here we went on this daring mission all the way to the moon, and what we ended up discovering in the end was the Earth.
Yeah, right.
You know, a lot of people give that photo credit for jump-starting the environmental movement. And actually, the first ever Earth Day happened just a little over a year after that photo was taken.
This is a CBS News special, Earth Day.
Good evening. A unique day in American history is ending, a day set aside for a nationwide outpouring of mankind seeking its own survival.
By the late 60s, our environment was under such stress, it was becoming harder and harder to ignore.
This planet is threatened with destruction, and we who live in it with death. The heavens reek, the waters below are foul, and we and the world, which is our home, live on the brink of nuclear annihilation. We are in a crisis of survival.
In the US, rivers had literally caught on fire from pollution, and people said that breathing in the air was like smoking 2 packs of cigarettes a day.
Yeah, but fast forward half a century later, and we're dealing with similarly intense environmental impacts today. And a lot of them may not be as visible, but in many ways, they're kind of even crazier.
Crazier than rivers catching on fire?
Well, more global at least. Rising seas and extreme weather like hurricanes are threatening some of our major cities.
Last night, New York's rivers surged above the banks of lower Manhattan with a rapid...
Many of the world's richest habitats, like the Great Barrier Reef, are under threat.
The extreme bleaching event is likely to kill some of the world's most pristine coral.
And 8.5 million metric tons of plastic are entering our oceans every year. We humans are having a bigger impact on our planet than ever before, to the point where...
We're at a sort of tipping point, because even 200 years ago, you wouldn't say that human activity is transforming the planet. Now, suddenly it is.
Who's that?
That's David Christian, a professor of history at Macquarie University in Sydney, Australia. So Christian isn't any kind of historian, he's a big history historian. This guy can explain the history of the universe in about 18 minutes.
So big history is an attempt to tell the history of the entire universe, and it links together lots of different historical stories, many of them from the sciences. So cosmology, geology, planetary science, biology, evolutionary biology, anthropology, and human history. And it brings them all together to create something that's a bit like a modern science-based origin story.
So Christian looks at the stories of humans, the planet, and the universe in about as wide a context as you could imagine. So everything from the Big Bang to the history of the 20th century. Anyway, he was talking about how human activity is affecting the Earth.
Our Earth was formed 4.5 billion years ago. Life appeared about 3.8 billion years ago. And very quickly, the sort of envelope of life appeared around the Earth, the biosphere, as we call it.
And you and I, we're all a part of it.
We humans are a product of the biosphere. I mean, we evolved through the same mechanism as any other living organism, through natural selection. Our food comes from the biosphere, our energy comes from the biosphere. We're part of this huge mechanism. But we're a very strange part of it.
We're a strange part of it. How so?
Well, humans have only been around for a tiny fraction of the Earth's history. If the history of Earth was shrunk down to the length of a 24-hour day, humans would have shown up in about the last 17 seconds. And yet...
some tiny difference, we're not entirely sure what it is, means that our impact on the biosphere is greater than that of any single organism in 4 billion years.
In fact, our effect on the biosphere is so significant, scientists have even come up with a new geological epoch for it. It's called
the Anthropocene, the era of the Earth's history in which the most important force for change is human beings.
Where the most important force is us. I mean, shouldn't it be volcanoes or locusts or something? Surely we're not that powerful.
Well, we're changing the composition of the atmosphere. We're changing the land usage of entire continents. And we're causing species to go extinct, even in some of the most remote places. From uninhabited islands in the Pacific to the North Pole, you can find telltale fingerprints of the impacts humans are having on our planet.
So this is an astonishing moment on a scale of 4 billion years. And it's also slightly scary because, quite frankly, the species that is now taking decisions that will determine the future of the biosphere doesn't really know what it's doing.
That does sound a bit scary.
Yeah, it does. But it wasn't always like this. In fact, in the span of human history, this all happened in the blink of an eye.
So how did we humans go from a species that lived in small pockets of Africa to one that has over 7 billion people spread across every continent?
You mean, how did we get to a place where one species is having such a profound impact on the planet? Well, luckily, this is exactly the type of thing that David Christian looks at.
What is it that makes us so different? I mean, why? You wait 4 billion years and suddenly a species pops up that can do this.
And according to Christian, our story begins with energy.
Energy?
Yeah. So energy is all around us. And at the core, life is about taking energy in from the outside and transforming it in useful ways.
So every living organism needs to suck in energy if it's to survive and reproduce. It's part of being a living organism. And Darwin tells us that the ones that won't pass on their genes. So we know from this that every living organism acquires genes which tell it to take in stuff from the environment.
So without energy, there would be no life?
Yeah, it's as simple as that. Since the first basic life forms began over 3.8 billion years ago, through random mutations and the slow tick of evolution, life has evolved into unimaginable complexity. But whatever species we're looking at, from hippos in Africa to Amazonian spiders, every life form has just a slightly different strategy for harnessing energy. And we're no different. Now, so the big question is...
where does that energy come from?
Where does it come from?
I mean, life needs energy to exist, right? But where does the energy that supports life come from?
I don't know. I mean, I guess from food, from nutrients, the things we eat?
Well, you're partly right, but food is really just a carrier of energy. It's not the source of the energy itself.
Then I don't know.
Ultimately, it comes from the sun. The sun emits huge amounts of energy into space. Some of it comes into Earth. It's captured by plants through photosynthesis. And that is the energy that drives the activities of the biosphere. Herbivores eat plants, carnivores eat herbivores through the food chain.
So, for example, birds eat caterpillars, caterpillars eat leaves, leaves that get their energy from the sun.
Oh, I get it. So owls eat squirrels, squirrels eat nuts, nuts that come from trees.
Yeah, exactly.
Humans eat cows, cows eat grass.
Yeah.
Foxes eat birds, birds eat frogs.
Yep, that's enough, Kevin.
Frogs eat snails, snails eat
Kevin?
dandelions, hawks eat snakes. So with all the food we or other animals eat, you mean ultimately if we keep tracing the source back, the original energy always came from sunlight-powered photosynthesis?
Yeah, exactly. So whether we're eating fruits that grow on trees, grains, or meat, all of the energy we use for our basic survival comes from photosynthesis. And photosynthesis is happening all around us. It's kind of like...
Like nature's magic?
Yeah. By using energy from sunlight, plants and some microorganisms, they can convert water and carbon dioxide into glucose, a simple sugar that plants use as food. Plants then use this sugar as an energy source to build leaves, flowers, fruits and seeds. All animals depend on this energy, but they can't make it themselves.
So plants, by using photosynthesis, are kind of like nature's food factories?
Exactly. Like mini food factories that drive virtually the entire biosphere. If photosynthesis disappeared tomorrow, almost all life on Earth as we know it would vanish, including us.
Okay, so we humans get our energy, like almost all other species, ultimately from sunlight. But that still doesn't explain why we're impacting the environment more than any other species. What sets us apart?
Well, for most of our existence, the truth is we humans weren't really anything special.
We weren't?
No.
Humans have been around for 200,000 years, roughly speaking. For most of that 200,000 years, we lived as foragers in small communities that had a limited impact on the environment.
We humans, like other animals, existed in a kind of symbiosis with the biosphere, as one tiny part of a big interconnected system. We had our own unique methods for capturing that energy for our survival. Our strategy was, as they say, hunting and gathering.
So we were kind of the jacks of all trades of finding food, right?
Yeah, we were masterful. And as hunters and gatherers, it was essential that we had a deep understanding of our environment. It was a matter of survival that we knew the seasons, how to work together to hunt animals, which plants and berries were safe to eat, and where we could find them. In other words, we needed information.
If you're a living organism, you need information to know about where the energy is in your environment. So every species uses information in order to get food and energy from their environment. Even bacteria do this. But there's a limit to how much information they have.
Some species obtain this information through their senses, and more social beings can even share knowledge about their environment with one another. Honeybees, for example, perform a dance.
A dance?
Yeah, you can see it online. Worker bees literally do a little waggle that tells their fellow bees in the colony where a good source of nectar is. So the more information you have about your environment, the more successfully you can capture energy from it.
But you still haven't answered my question. What is it that makes us humans so different to all the other animals?
Well, quite simply, as David Christian puts it, it all comes down to...
language. We're so clever because we can share information in a way no other species can.
Bees may dance, but we humans, we have language. We speak, we write, we sing. We have so many ways of communicating.
Now, somehow or other, and we still don't quite understand why, the first members of our species developed a linguistic capacity that meant that we could share information with a precision and a volume that was utterly new. Then what happens is, if I have a smart idea, I pass it on to you, you pass it on to someone else, I die, but the idea lives.
And it allowed us to not just share information in the short term, but over time.
Einstein took mass and the speed of light and expressed their relation to energy in a simple equation.
And that's what makes us different. The fact that we can share information so well that information can accumulate, and it can't accumulate over generations for any other species. So this information is what gives us increasing control over our environment, over energy flows, over resource flows.
Now, as we said earlier, all plants and animals have their own strategy for harnessing energy and surviving. But we humans, we did something different. As we accumulated more information, we changed our strategy. What we did, starting around 10,000 years ago, independently in different parts of the world, is we hunter-gatherers, we started to farm.
Right, so you mean we started to plant things?
Yeah, but not just that. We also began to domesticate animals like goats. At first mainly to eat, but soon we used cattle and horses to help us work and just get around. And at the end of the day, what we were doing with agriculture still comes down to energy.
What humans were doing by farming was basically grabbing more and more of the energy flows that were going through the biosphere. And one of the things that farmers learned is that if you put a lot of hard work in, you can change your environment so you get more of that energy that's coming from the sun.
And how are we doing that? How are we grabbing more energy?
In one word, manipulation.
So what farmers do is they manipulate their environments, they manipulate the plants and animals around them, so as to get rid of the ones they can't use and to increase the production of those like wheat or rice or sheep that they can use. End result, energy comes into the biosphere through photosynthesis. We humans get a larger and larger share of that energy.
So does this mean that thanks to agriculture, we had a more regular supply of food?
Yeah, and because we were now more tied to where we grew our food, agriculture meant we established more permanent settlements. Plus, since we no longer collectively had to spend so much time foraging, it freed us up to do all sorts of things. This extra energy we now had control over is what allowed modern civilization to develop, along with all the things that came with it.
So agriculture spreads, we get more control over energy, more control over resources. End result, we get more people, more cities, more villages, more towns, states, empires. All of that stuff depends on agriculture.
So agriculture fundamentally changed the world. It was a turning point in human history. The invention of farming explains how we started to have such a big impact on the biosphere. By manipulating the environment to suit our needs, we were able to capture more and more energy, grow our numbers, and thrive as a species.
Well, agriculture was a big deal, and it definitely sets us apart from other animals, but it still doesn't really explain the full story.
It doesn't?
No, I mean, farming was around for 10,000 years, but for most of that time, we didn't have all the things we have today. Agriculture can't explain how we got trains, planes, automobiles, skyscrapers, the internet, and 7 billion people. Today we have such an abundance of energy that we don't even think about where it all comes from. We just turn on the light, press the button on the washing machine, plug in our phones, or get on the tram without much thought. But it wasn't always like this. Back a few hundred years ago, our energy didn't come so easily to us. And to really explore what it was that changed, we have to take a trip back in time to 17th century Britain. Back in Britain in these times, most of the population was rural and poor. The vast majority of Brits worked on the land, and unlike today, there weren't any magical sources of energy we could just flick on in the morning. Basically, if we wanted to do or make anything, we had to do it by muscle.
By muscle?
Yeah, would hammer the metal into shape, weave the cloth, chop the wood, plant and harvest the crops, or walk the 15 kilometers over to the next town.
Oh, that sounds exhausting.
Right? And so despite agriculture's long reign, if we really dig down to it, the average family was still living pretty much as they had for centuries.
The knowledge that the harvest was going to be good was the biggest single sign that the community would be relatively prosperous. The knowledge that the harvest was going to be bad signified constraint, and if it's bad enough, very poor conditions for those closest to the precipice.
That's retired Cambridge professor Tony Wrigley. He's the author of the book Energy and the English Industrial Revolution. The harvest, more than anything else, determined the basis for our wealth. And this dependence on the harvest is what Tony Wrigley calls the organic economy.
The organic economy? What does he mean by that?
Yeah, organic didn't mean that we all shopped in the organic section of the grocery store. It meant plant photosynthesis is what was responsible for everything we had in our economy.
You mean food?
No, it wasn't just food, it was everything. everything produced or consumed. The hide and wool we use to make clothes with had to come from the harvest. The hay we used to feed the cattle and horses that we depended on to plow our fields and move us around, that had to come from the harvest. Everything, all production in some way or another, could be traced back to the process of farming. Until recently, this reliance on the harvest was something that characterized every single economy in the world.
All right, well, that sounds like a good thing, right? I mean, a hard life, but at least it's sustainable.
Well, compared to now, it was more sustainable. But the problem was we could barely get enough to survive. You see, the thing is,
there's a limit to how much energy you can get through farming.
That's David Christian again. Farming gave us a lot more energy, but it didn't give us infinite energy.
And by the 18th century, some economists are saying, we've now covered the entire surface of the earth with arable land. There's a limit, so growth is going to stop for us humans.
Even famed economist Adam Smith believed this.
Adam Smith wrote about growth. He was one of the first modern economists for whom the idea of growth was fundamental. But he said, and he was not the only one, growth is going to stop. We're going to do what all other species have done. Eventually we're very clever, but we're going to run out of resources once we've filled the earth with farmland and woodland, because that's where we get our fuel from. It'll all stop.
Well, I guess that makes sense. It just seems so unlike today, when all we hear about is growth, growth, growth.
The economy is picking up speed. The sum
Britain's
total of all that we
sped up
produce
at the
from
end
a
of last
car
year,
to a
expanding by...
Exactly. It's kind of hard for us to wrap our heads around. Tony Wrigley puts it like this.
One of the problems of living in a post-industrial revolution world is that it's just a very foreign concept. It doesn't seem natural to have to accept that you're stuck where you are, so to speak. And therefore, you need initially a sort of leap of the imagination to put yourself back in the constraints of an organic economy.
A great example of the kinds of limits that existed in organic economies and what it meant for the average person is told by a story of wood in Britain. In British society, back at the start of the 17th century, wood was indispensable and had been for centuries.
Wood was the sole source of heat energy, and of course heat energy was essential to keep houses warm in winter and to cook food and so on.
And wood was a key resource for industry. It was used to make ships and for building homes. Burning it is what provided the intense heat energy needed for brick making, glass making, and for smelting all types of metals. So wood was an essential part of life. But like everything else that existed in the organic economy,
you had to grow it.
Exactly. And if the growth rate of trees wasn't enough to keep up with all the wood that people were chopping down and using,
you had a problem?
You had a really big problem. Your houses go cold, your industry grinds to a halt, things get pretty desperate. And Britain, around this time, was starting to run into this problem.
Wood in forested areas had been declining for a long time, and it was producing extreme difficulties.
In the early 17th century, the government was scrambling to stop deforestation. Wood prices soared, and wood became unaffordable for the poorest of the population. So Britain desperately needed a new source of energy. Turns out, Mother Nature had an ace up its sleeve, because it just so happened that in many of the same areas where woodlands were getting desperately short, a certain black rock peeked up through the Earth's surface. Just like wood, you could set this rock on fire, and it would release heat.
A rock that burns?
A rock that burns, and I think you might have heard of it. That little black rock was called coal.
Oh.
I actually have a piece right here. Now, I know it doesn't look like much, but this tiny rock has a big history. It was 300 million years ago, before the time of humans, before the time of even mammals, during what is now called the Carboniferous period.
The what?
Carboniferous, which literally means carbon-bearing. Now, this was a pretty unreal time, one where gigantic bugs such as dragonflies with wingspans of 75 centimeters and caterpillars up to 2.5 meters long made their mark.
Caterpillars over 2 meters long? That sounds kind of terrifying.
Right? Anyway, during this period, trees were relatively new evolutionary arrivals, and the microbes that would decompose trees today when they die just didn't exist yet.
You mean so when they died, they would just fall over as is and kind of stay that way?
Yeah, exactly. But of course, more and more trees are growing in their place.
So trees die as they get buried, their bodies get fossilized, but they contain all this energy that they've sucked in through photosynthesis.
And over millions of years, with added pressure and heat, This organic material full of carbon was transformed into what we know today as coal.
Huh, I'd never really thought about where coal comes from. Wait, so coal is essentially fossilized trees?
It's kind of crazy, right? And it just so happens that Britain was home to a lot of these remains of ancient forests. Not only that, but the deposits were also pretty easy to get to. In many places, they came out right to the surface. It was a lucky quirk of geology. Now, humans had been using coal actually for thousands of years.
Coal had actually been dug sporadically and in small quantities right back to Roman times. It's not a completely new invention, so to speak.
But around the 16th century, with wood supplies getting so stressed, coal started to become a lifeline.
So people started to burn coal instead of wood?
Yeah, so it began to almost completely replace wood burning in places like London. It was dirty, smelly, and created thick smoke when it was burned. But using coal meant that people were now relying on an energy source that didn't have to grow each year. We were starting to escape from the dependency we had on the harvest.
If you have coal as a source of energy, you don't need to have woodland. Woodlands can contract a great deal without bringing disaster. So there are acres you can use, in a different way to produce food.
Some historians argue that coal saved Britain from a humanitarian catastrophe. But nonetheless, the shift from wood to coal at first didn't exactly seem like a revolution.
Oh, really? Why is that?
Well, as Tony Wrigley puts it,
initially, coal was simply used to do what wood did. You can boil a kettle just as easily with coal. It makes a nasty smell, but it's the same process.
We now had all this energy we could make use of, but there's only one thing we could really do with it. Use it for heat.
Well, that doesn't sound so bad. I mean, that's what coal is supposed to do.
Right. But for most things in our economy, both now and then, what we really need in order to make things is not just heat energy, but mechanical energy. The power to move, pull, bend, cut, and shape. And for all of that, besides a few limited areas where we had figured out how to use water or wind, we were still basically stuck where we had been for millennia, dependent on muscle power. Muscle is what plowed the fields, hauled our goods between towns, spun the wool, and hammered the metal.
Right, and all the heat energy in the world can't help you with those things.
Well, not yet. But at the beginning of the 18th century, something big happened. Something that fundamentally changed the way we use energy, and it started us on the trajectory to the world we live in today.
But the really key change, the thing that universalizes the use of coal for almost every productive purpose, for anything where you need to use energy, came about because of a problem with the coal mines.
With the shortage of wood, demand for coal in Britain was skyrocketing. But mine owners were facing a challenge.
What kind of challenge?
Well, mining at the time was pretty simple. A seam of coal would outcrop to the surface, people would notice it, start pickaxing, and just follow the seam along as it went deeper. But there was a problem.
You couldn't dig coal deeper than somewhere between 50 and 100 feet usually.
What, they couldn't dig down? Why not?
Well, as you dig down, pretty soon if you keep on digging,
you get below the water table, and what that then means is the seams of coal and the diggings by them are filled up with water, which is hopeless.
That's Jeremy Black, professor of history at Exeter University.
So what you have to try and do is to pump out the water. Well, the difficulty is you need some power source to pump it out.
They tried to use donkeys and horses,
literally horsepower,
to drain the mines, or men carried out buckets themselves. But there was only so much water that one could take out by muscle power alone. Mostly once they hit the water table, that was it. They had to give up on the mine.
So these problems were getting more and more problematic. So a lot of mine owners were very, very keen on a machine that could resolve that issue.
Who's that?
That's Irene DeBow, senior curator at the Black Country Living Museum outside of Birmingham, England. So they have this problem. But then along comes a man called Thomas Newcomen. Now, he's a small-town ironmonger. He makes and sells tools. And some of his biggest clients are the mine owners in Cornwall, in southwest England. Now, Newcomen learns of the problems with flooding, and for whatever reason, he's convinced that he can come up with a solution. Newcomen starts experimenting, playing around to see if there's a way that he can use the heat energy from coal to remove water from the mines. And after 14 years of experimenting, Newcomen comes up with a solution. It was rough, but it was a spark of ingenuity.
So how did this machine work?
Well, the engine worked by using the heat energy released by burning coal to boil water and create steam. Now, when water turns to steam, it drastically expands in size. That's why if you use one of those old school kettles, it whistles when it starts to boil. It's the pressure created by this increase in volume happening in a small confined space that causes that. And when steam cools and condenses back into water, the opposite happens. It drastically shrinks in volume. What Newcomen figured out was a way to use this property to move a giant piston.
A giant what?
A giant... You know what? I know who can explain it better than me.
This is what's called an atmospheric steam engine.
Here's Ben Russell, curator of mechanical engineering at the Science Museum in London.
So rather than using the positive force of steam to push, you put steam into a cylinder which is open-topped, and then you condense the steam. The steam creates a partial vacuum, and the atmospheric pressure pushes down the piston into the vacuum. That's why it's called an atmospheric engine.
So just the weight of the air around it?
Yes. And then that lifts these pump rods that go all the way down to a coal mine, and they pump the water free of the mine to make sure it doesn't flood, and you can get the coal out.
That sounds like it must have been like a dream come true.
Yeah, for mine owners, it was a godsend. It made such a difference that in the 1730s, a French coal mine reported that one Newcomen engine, with 2 people operating it just 48 hours a week, had replaced 50 horses and 20 men pumping all week long in round-the-clock shifts.
So what you're saying is, through Newcomen's engine, we could use the power of coal to harvest more coal?
Pretty circular, right?
Right.
And it meant that Britain now seemed to have basically unlimited coal.
Within 7 years, there were engines in Belgium, Austria, Sweden, Holland, France, Germany. They were built everywhere.
But the coolest thing about Newcomen's engine was, for the first time in human history, we had managed to take the heat energy from a fossil fuel and use it to do real mechanical work, things that we could only have done with muscle power before. So Newcomen's engine was transformational, but it did have one big flaw.
A disadvantage of this very early engine is that it uses an awful lot of coal. And when I say an awful lot, I mean an awful lot.
But now that people had seen what the combination of steam and coal could do, it didn't take much for inventors to start dreaming of an improved machine, one that could do even more.
And that's where James Watt, the Scottish engineer, comes in.
That's Ben Russell again.
Now, Watt is a Scottish Presbyterian. He's a religious man, and Presbyterianism ingrains in him a deep moral dislike of waste. Any waste is a bad thing for him.
Watt has a very multifaceted background.
He's trained as an instrument maker, making scientific and musical instruments. He's interested in chemistry. He does all sorts of things.
Watt was working at the University of Glasgow, and he's given a model Newcomen engine to repair.
And Watt has to fix it because it doesn't quite work very well. And this puts him on, he starts to think about, how can we make the engine better?
And so he's taking a Sunday stroll to the Green, a lovely park by the water in Glasgow.
And he has one of those very rare eureka moments.
Watt comes up with an innovation, the separate condenser, that allows the steam engine to do the same amount of work, but using far less coal. They actually have the original one at the Science Museum in London, where I spoke to Ben Russell.
Now, actually, we've got the very first one just here. I forgot about this.
It doesn't look like much, just a small metallic cylinder.
You could easily, it looks like a piece of pipework from someone doing some plumbing in your house. But actually, this is an object that changed the world in a very real and literal sense.
Not only was the new design much more efficient, but later on, Watt figured out how to transform the up and down motion of a piston into continuous rotary action.
So does that mean it goes around in a circle instead? Is that a big deal?
It might not sound that important, but that small change opened up all sorts of possibilities. Now the combination of coal and steam could do more than pump. It could power all sorts of early machines, which were previously powered by man, animals, or water alone.
Suddenly you've got available a steam engine, which can make a very efficient use of energy, which can be available pretty much anywhere where you can get coal and water to.
James Watt invents his improved steam engine. This is the first steam engine that was efficient enough to be usable.
Now for all sorts of things, you're able to turn
fossil fuel energy into mechanical energy.
And then from that you get factories, mills, all these sort of places which start to depend upon steam power.
Soon, steam engines were used in all types of industries, and manufactories, which were the first factories powered by this new source of energy, spread out all over the place.
And then you've got the setting for what's in a way rather unfortunately called an industrial revolution. It was a revolution in all aspects of production.
In things like textiles, what used to take dozens of people working separately could be accomplished just by a few people tending a few steam engines.
So it's a real turning point. Watt's engine is one of the pivots, one of the hinges upon which we swing into the modern industrial age.
Over the next few decades, steam engines got more and more sophisticated, and they found themselves in more and more applications. With the invention of high-pressure engines, we soon had locomotives and steamships. People and resources could now move between places with a speed and an ease that would have been previously unthinkable.
So steam speeds up the world, and the world speeds up with all the consequences that brings.
And because we had all this free energy stored from hundreds of millions of years before, it meant growth didn't have to stop.
In fact, it got faster. Growth got faster and faster and faster.
And remember, fossil fuels like coal are still energy from sunlight. But now, instead of growing our energy each year through the harvest, we were using energy from the sun that had been gathered and then buried over millions of years.
Instead of tapping into 1 year's worth of photosynthetic energy, you're tapping into 300 million years worth of that stuff.
And compared to before, to when we were dependent on the harvest?
It's an utterly different scale. So it's like a bonanza, it's like a gold rush. It's as if we'd struck gold in terms of energy.
Now, we weren't dependent on the harvest to provide the bulk of our energy, but on fossil fuels. They were what we used to move our goods, plow our fields, drive our factories, melt our iron, and later on, create our electricity.
And what did this mean for farmers, for the peasants that worked the land?
Well, with this growth and new energy, Britain completely shifted away from a society built around subsistence farmers to an urban landscape of wage earners.
You know, people moved into industries and therefore had an entirely different way of living. They lived in different circumstances. They were no longer in small villages. They were in big cities, big societies.
And that's what happens in Britain. You know, between 1760 and 1820, Britain goes from being a country which is primarily agricultural and rural to one which is, to a large extent, industrial and urban, which is an amazing achievement in, 3 generations. And Watt is central to that, and his engine is as well.
Most people's lives were still really hard. We worked long hours in conditions that would now seem unbearable. But because production exploded, the average person also began to have access to all kinds of goods that would have been previously unattainable.
You would have more things where you lived. You would have, even relatively poor people would have more things around. A teapot, a chair.
And just think about how fundamental a change this was. We take it for granted, but it was as if the folktales that people had dreamed of had somehow become a reality.
Fossil fuels have brought an incredible amount of good into our world, I think.
That's Rob Hopkins, environmentalist and founder of the Transition Towns movement.
I liken them to the magic potion in the Asterix books. These sort of French-Belgian books about these Gauls living in the time of ancient Rome, and they had a druid in their village who was able to brew this magic potion that gave them all superhuman strength.
With stirring motion, I mix the potion that gives us our magic powers. The magic potion that increases your strength 1,000-fold. Exactly what do you...
Fossil fuels have really been a magic potion for us. You know, it enables us to do things that were previously completely unimaginable. You know, the idea that you could have this pot where you just said a magic word and it would just fill up with food without you having to do anything, or the 20-league boots that the giant had that you put them on and you could stride across the planet, or the elves and the shoemaker, you know, where you went to sleep and then these elves came along in the night and did all the work for you so you didn't have to do. Well, fossil fuels really became all of those things and transformed our sense of what we thought was possible.
All of this was great. And so for the next 200 years, our use of and dependence on fossil fuels just continues to expand.
The Industrial Revolution, fossil fuels technology spreads around the entire world.
Thanks to the steam turbine and coal, in the late 19th century, we developed electricity. A few years later, thanks to oil, we developed cars, and then planes. Now fast forward to the mid-20th century, when
everything really goes strange.
Strange?
After the Second World War, you can see a lot of changes generated by fossil fuels.
By the 1950s, industrialized nations had transformed into gigantic pillars of consumer culture.
Right, so this was like the heyday of plastic when all those new appliances came out.
Tupperware. Never before has this type range been offered at such a low, low price.
The suburban dream of a house and a car were becoming a reality for more and more people.
This Laundromat 25 is fully automatic.
Exactly. The huge resources of energy we had learned to tap had by now transformed the world into something that would be unrecognizable to someone living in 1750. This is what many people call
the Great Acceleration.
This was an acceleration built upon an acceleration.
Most of us have real difficulty grasping the scale and speed of change, and there's a very good reason for this, which is the way we're taught about the past is on all the wrong timescales.
Right, and I guess all this happened in just a tiny fraction of human history. 200 years is nothing on the scale of this planet.
Yeah, exactly. Which is why we need to look at the big history again, which David Christian knows all about.
So you really need to look at the history of the biosphere over thousands or millions of years before you can see how weird are the things that have happened in the last 100 years.
A great example is to just look at the total population of our species. I mean, for most of our roughly 200,000 years on this planet, the human population was tiny.
Yeah, like 10,000 years ago when agriculture first emerged, they said there were only like a few million people on Earth.
Exactly. But with the spread of farming, our numbers started to climb, so that by the height of the Roman Empire, there were over 200 million of us.
It's amazing.
But it's nothing compared to what happened next. In the year 1800, the world population was roughly 1 billion. Now, it took all of human history for us to reach that 1 billion number, but with the Industrial Revolution, it skyrocketed to over 7 billion people just 200 years later.
So you're saying it took 200,000 years for us to reach 1 billion people, and it took just 200 years for us to add another 6 billion?
Pretty incredible, right?
Wow.
So what this means is that if you graph human population over a really long time, it looks a bit like a hockey stick.
So now you can imagine a hockey stick. The handle of the hockey stick goes back 1 million years. The end of the hockey stick shoots up in the last 100 years.
And it's not just for population. You can find these hockey sticks for just about anything.
There are hockey sticks that shoot up for energy consumption.
The number of livestock.
For buildings.
The amount of aluminum.
So aluminium is a new element that appears on the surface of the Earth. So you can draw a hockey stick. There were no plastics before. So this is again one of those hockey sticks where there was nothing. Stainless steel never existed before. Concrete. It's an entirely new type of rock.
And on and on.
Huge numbers of things.
But the point is
that suddenly, in the last 100 years, a lot of processes have accelerated, and they are now on such a scale, they're moving so fast, that they are beginning to disrupt the mechanisms that have kept the biosphere relatively stable for a long, long time.
And it's having all sorts of consequences.
Other species are beginning to decline. Rates of extinction are now faster than they've been probably for 60 million years. So things are changing very, very fast indeed at the moment.
So why? Why, after 200,000 years of human history, does it all suddenly accelerate in the last 100 years?
I think I know the answer.
Immediately, in the short term, it's fossil fuels.
Fossil fuels underpinned an exponential growth of everything: population, food production, urban expansion.
The whole thing's gone a bit crazy because of this colossal flow of energy from fossil fuels.
Okay, so if we're talking hockey stick measurements, then you forgot one massive one on your list, Kevin.
I did?
Yeah. One of the most important and scary is the concentration of a little molecule called CO2, or carbon dioxide. Carbon dioxide makes up just a tiny percentage of the atmosphere. We can't see it, but it's all around us, and it's fundamental to life.
Right, plants use carbon dioxide in photosynthesis to make the nutrients which drive virtually the entire biosphere, right?
Yeah.
And thanks to quirks of geology, some of that carbon got buried and transformed into fossil fuels.
Exactly. But when we burn this coal, oil and gas, it's like we're running photosynthesis in reverse. And in releasing this stored energy, we're putting this carbon dioxide back into the air.
Well, there's a natural flow of carbon. I mean, carbon dioxide is in the atmosphere naturally anyway. And it's that natural level, along with some other greenhouse gases, that provides the Earth with this nice warm blanket that allows life to live on this planet.
That's another Kevin.
Another Kevin.
I'm Kevin Anderson. I'm Professor of Energy and Climate Change here at the University of Manchester.
Without CO2, the world's average temperature would be 30 degrees colder.
So if it wasn't for the greenhouse effect, we wouldn't live here. We'd be minus 18 degrees would be the average temperature of the planet, so quite a cold place to live.
Would be ruled by penguins.
Or more likely, there would be no us.
Oh, that is worse.
But, like all ingredients, what was good in moderation can ruin the dish. And when we add more CO2, it means the Earth starts to heat up. And what happens when you measure these concentrations of CO2 over time?
Let me guess, like all the other hockey stick graphs, it shows that they've started to climb?
Bingo.
How do we even know this?
Well, actually in a kind of incredible way, from ice cores in Antarctica.
What? From ice cores? What do ice cores have to do with anything?
Well, because new ice forms over eons. Scientists can actually dig down kilometres into the ice sheets, and they can get a record of what the atmosphere was like over hundreds of thousands of years.
What happens is, year by year, bubbles are trapped in ice cores, and each of them contains a little mini sample of the climate at that time.
That is so cool.
I know. Now, the concentration of CO2 is small.
How small?
Small enough to be measured in parts per million, or ppm.
And so what did the ice cores show?
Well, they showed that as far back as 1 million years ago, CO2 concentrations have never gone above 300 ppm.
And what are we at now?
All I can say, that number now is over 400. So it was, it's a big increase over what it was before we started burning fossil fuels.
And so do we know it's us, though, that has caused this rise?
Yeah.
And we are very clear that it's the burning of fossil fuels that has increased the amount of carbon dioxide in the atmosphere. There's a special, if you like, a little fingerprint, an isotopic fingerprint, which shows what's fossil fuel burned carbon dioxide and what's, if you like, natural carbon dioxide.
So what are the impacts of this extra bit of CO2?
Well, because of CO2's role in the greenhouse effect, it's as if we're adding more and more blankets to the Earth. We're better insulating it.
So is this something that we can already see? Are the temperatures of the planet going up?
Actually, yeah.
We know that the temperature is rising. We see that empirically from our observations around the globe. We know it's going up definitely from the burning of fossil fuels and from the other anthropogenic human greenhouse gases.
And so by how much have temperatures gone up so far?
So we've had about 1 degree of warming so far.
Who's that?
That's Miles Allen, leader of the climate research program at Oxford University.
Well, 1 degree, that doesn't sound like so much. And I mean, I wouldn't mind winters that are a tad warmer.
Right? But these temperature rises, they come with some pretty terrifying consequences.
And what we're now starting to see are quite significant changes in the climate. And we can see that the levels of climate change that we've already started to witness are already having detrimental effects.
What we're seeing is climate change loading the weather dice, if you like, towards some kinds of events and away from others. So the kinds of events that are being made more likely are heat waves, intense rainfall events, flooding, for example.
At 1 degree of warming, we've got rising sea levels. We can cope with them at the moment, but they're getting worrisome in some places.
That's Tim Flannery, head of the Climate Council in Australia.
Are we getting increased heat waves in places like Australia that are killing lots more people than they did before? Longer, hotter, more frequent heat waves?
It's simply unbearably hot, with hot wind blowing at you.
We have other changes, droughts, for example, in some parts of the world, drying out that's being caused by this. We're having extreme storms in other parts of the world. So we're living in a shifting world at 1 degree of warming.
But it's just the beginning.
We are certain that we're going to see an increase in these level of impacts as the levels of emissions continue to rise, the levels of carbon dioxide in the atmosphere continues to increase, and that as those impacts arise still further, we're going to see many more people impacted around the globe.
There are some areas in which we can get a bit of a grip on what the world may be like. So what climate change scientists do is they look at different scenarios for the future. And one of those scenarios is we keep using fossil fuels at the rate that we're using them now, and we actually have a pretty good idea.
The current projection of where we're actually heading if we carry on as what we call business as usual is we're probably going to head towards something like a 4 degrees C temperature rise across this century as a global average. The implications of that are huge. So a 4 degrees C global average would mean during heat waves of 6 to 12 degrees C warmer than the heat wave would otherwise be and prolonged. significant increase in flooding, massive increase in sea level rise across this century, probably a metre, maybe even more than that, but also locking in many more metres, probably 7, 8, 9 metres more for the next quite a few hundred years as we melt Greenland and some other parts of Antarctica.
I guess goodbye small low-lying states.
Not just that, goodbye Shanghai, goodbye Manhattan, goodbye Amsterdam, goodbye London, goodbye Mumbai.
And given that a large proportion of the 7 billion people who live on Earth live around the seashores, they're going to have to move.
Models predict most of Miami Beach could be underwater by the end of the century.
4 to 6 degrees of warming would literally make parts of the world uninhabitable.
It'll be hotter, it'll be warmer, climate events will be more violent. Agriculture, all the rules about agriculture will change. So this is frankly a very scary scenario.
So we know from the science that if we carry on doing what we're doing today, that we will be living an apocalyptic future for future generations and indeed even for our own children.
So of course we all want to avoid an apocalyptic future.
Seems reasonable.
And that's why in 2015, world leaders came together to sign what's called the Paris Climate Accord, a treaty aimed at preventing a global catastrophe. And it had the goal of keeping global warming to well below 2 degrees. 2 degrees is what many scientists say is the highest average temperature the Earth can handle without significant disruption to human civilization.
So does that mean if we stay below it, we'll be safe?
Well, even 2 degrees will still have a huge impact.
Well, we want to try and hold the temperature rise across the century to no more than 2 degrees centigrade. And to just put that into some sort of perspective, the difference between now and an ice age is about 5 degrees. So a 2 degrees centigrade rise across just a number of decades is a phenomenally fast rise in temperature.
Effectively, when I think about it, I imagine myself looking down on this spinning, beautiful blue globe of ours, and we can see the two polar ice caps, and we can see the shapes of the continents, and we can see the distribution of rainforest and deserts and things, the current world we know. At 2 degrees, all of that changes. The northern ice cap is gone. The southern ice cap changes shape. The continents change shape because we've got rising sea levels, flooding low-lying areas. The distribution of plants and animals around the world shifts. The rainforests are going to shift. The deserts will shift. The temperate areas will all shift. So we're really talking about creating a world by 2 degrees of warming that, we haven't seen anything like it for 5 million years probably on the planet. It's long before humans ever existed.
And let's be clear again, at 2 degrees C temperature rise, many people will die. They'll be poor, typically non-white, very low emitters who have not had any part in this problem at all.
But it's not all. I have some other bad news, because we don't have much time.
By 2030, at current rates of emission, we'll be committed to 2 degrees of warming.
So unless we actually make some very significant changes quite quickly, then we're going to breach this 2 degrees C rise.
Oh man, 2030 isn't far away at all. But so will the Paris Agreement help us get there?
Not quite.
With the Paris Agreement, if every country honours what they've currently put on the table, we will be committed to about 3.5 degrees of warming by the end of the century.
It still won't be enough.
So clearly something has to change.
And fast.
And we know what we need to do, but we've just not had the courage to go ahead and do that. What ultimately we'll have to do is to reduce our emissions. And every year we fail to reduce them, then the following year it gets even more difficult.
And how can we do that, given our dependence on fossil fuels? I mean, we get almost all of our energy from them.
Take away fossil fuels, and our lives would go back to those of a medieval peasant. Just overnight. It's as simple as that. Everything around us in the modern world depends on fossil fuels.
And I've got more bad news.
Oh my God.
Because we don't just need to reduce our emissions, we need to get them down to zero.
It's very important people to understand that stabilising climate at any level means stopping putting CO2 in the atmosphere. The carbon dioxide we are dumping into the climate system at the moment will still be affecting climate in 10 to 100,000 years' time. So it's this permanence that really changes the picture, because it means it's not enough to reduce emissions by 20% or 50% or even 80%. You've got to reduce emissions to net zero to stabilise the climate.
And because we've left it so late, we have to make some pretty drastic changes to our economy.
So by 2050, if we are serious about this 2 degrees C framing, then we would have to be zero carbon energy, not just electricity. That means our planes, our ships, our fridges, our cars, every facet of our life would have to be zero carbon energy, which is a huge challenge. oil and coal and gas are so ubiquitous, they're everywhere in our society. To make that full-scale transition in the time frame we have to avoid dangerous climate change is going to be really difficult indeed. But I would say essential.
For we meet in an hour of change and challenge, in a decade of hope and fear, in an age of both knowledge and ignorance. The greater our knowledge increases, the greater our ignorance unfolds.
5 decades on from the Apollo 8 mission, the world is still in turmoil, only in a different way.
The ecological footprint of humans can easily be seen from the International Space Station.
You can see the megacities, you can see the constant haze of pollution from the burning of coal, and you can see the forests that have been cleared for livestock.
But maybe the biggest and longest lasting of our impacts is what you can't see, the extra carbon dioxide we're pumping into the atmosphere, an invisible gas which is threatening to change just about everything about our world.
It's kind of a remarkable story, how we ended up here.
And it's kind of interesting to think of how it was knowledge that got us here.
What do you mean knowledge?
I mean, it was through the accumulation of knowledge that we learned not only the art of agriculture, but then how to make the steam engine and learn how to harness the energy of fossil fuels. To the point that, before you know it, we're sending gigantic rockets into outer space.
Houston, contact with a test 1. No man can fully grasp how far and how fast we have come. But condense, if you will, the 50,000 years of man's recorded history in a time span of but a half a century. Stated in these terms, we know very little about the first 40 years, except at the end of them, advanced man had learned to use the skins of animals to cover them. Only 5 years ago, man learned to write and use a cart with wheels. The printing press came this year. And then, less than 2 months ago, during this whole 50-year span of human history, the steam engine provided a new source of power. Last month, electric lights and automobiles and airplanes became available. And now, if America's new spacecraft succeeds in reaching Venus, we will have literally reached the stars before midnight tonight. This is a breathtaking pace, and such a pace cannot help but create new ills as it dispels old. New ignorance, new problems, new dangers.
So knowledge is what got us here, for better or for worse.
But it's also knowledge that will get us out of this mess.
We have so much knowledge now, and we do have a huge amount of energy, that it may be that this is an opportunity, not just to avoid something horrible, but actually to use our skills and use the huge bonanza of energy that we have in a controlled way to build much, much better society. So that's the positive way of thinking about this. And we have the skills. We have many of the skills needed to do that. I think we're not thinking creatively enough. We need a hell of a lot more thought about what a more sustainable world will look like. What will a world that's not utterly reliant on this bonanza of fossil fuels, what will it look like? It's just a fantastically complex problem. But if any species is equipped to navigate a pathway through this, it's surely us. Because now collective learning is operating at warp speed. So it'll be a very, very different world, but we need to think very creatively about what that world will look like, as well as how to get there.
It kind of seems overwhelming, all that uncertainty, the scale of the problem, like an impossible feat.
But so did sending a man to the moon. I mean, when JFK first set America on a course towards the moon in 1961, there was also no guarantee that it was doable.
We set sail on this new sea because there is new knowledge.
Thousands of scientists worked together to get those men to the moon. And it was a big investment. New technologies were invented, new techniques. And in the end, just a few years later, they got there.
There's that majestic plume of flame behind the Saturn V. As she
And the whole
thunders
world got to see the Earth in its true context.
It had a huge impact, I think, to the people to see their home in its true light. Even though they knew the thing was taken 240,000 miles away, it really emphasized the fact to people that this was Earth and this is their only place to be.
It makes you realize just what you have back there on Earth. The Earth from here is a grand oasis of the big vastness of space.
And so it told me two things. It told me, one, how insignificant we really all are on that small body that is orbiting a rather normal star in the outer edge of a Milky Way, a galaxy, and also how fortunate we all are to be there. As a matter of fact, it kind of reminded me that instead of going to heaven when you die, you actually go to heaven when you're born. You arrive on a planet of the proper mass that has the gravity to contain water in an atmosphere that is just the proper distance from a star, our sun, not too far out to be too hot or too cold, just the right distance that we can absorb the sun's energy. And that, of course, was how life evolved in the beginning.
So, if we can send a man to the moon, surely we can solve this problem as well, especially since we're now acting as one world instead of one nation.
I don't know. Our whole world, our economy, it's dependent on this energy. How can this change in just a few decades?
The crucial thing that happens is obvious. We have to wean ourselves off fossil fuels. But what does that really mean?
Well, that's a very big question.
And one we're going to explore on this season of The Elephant.
In future episodes, we're going to be exploring how scientists, entrepreneurs, and communities are working to close the gap between our world's thirst for energy and our need to get our emissions down to net zero, because there are a lot of people working on this. So we're going to be bringing you stories that take you inside potential climate change solutions, exploring everything from new science and ancient wisdom to emerging technologies that might just hold the key to us solving this crisis. From electric helicopters and smart grids to the farms of the future. I hope you'll join us. This was The Elephant, with me, Kevin Caners.
And me, Charlotta Lomas.
See you next time.